Yes. Okay, can everyone hear me? Great. So first of all, a short disclaimer. The title says that I'm using the within individual variability in the MR, but I'm actually just using the model, the Scammell's model that you all know so well, to get some instruments for my Mendelian randomization. So it's not exactly the within individual variability that I'm looking at. It's more the general variability and how I could use that in Mendelian randomization. I don't work on this alone. Is it working? I work with Steve Burgess on this, and of course with those two great organizers of this workshop, with Marco and Jessica. And I know you guys probably don't know everything about GWAS and genetic models, so I thought first a short introduction what I'm actually talking about. So maybe the discussion later would be easier to do. So I will be talking about SNPs and GWAS. So a SNP is just a single nucleotide polymorphism. So that means that in a specific location in the genome, there's a variability of what alleles could be present. And we look at them and we can say, okay, we have typically two alleles possible. So one from your mother, one from your father. And the combination of those two alleles is your genotype. So you can have 2 times the A allele, 2 times the B allele, or you have a mix A and B. You can't differentiate between the mother and the maternal and paternal allele. So we have just AB. And what this GWAS is doing, that's standing for genome-wide association study, is simply to test all millions of mutations in your genome for association with whatever trait you're looking at. Can be a biomarker, can be a disease, whatever you're looking for. And what I mean with additive effect is you assume that every count of B allele is increasing something. So in this example, every B allele increases your mean level of your biomarker. And this is done by a simple linear regression model, no problem. So that's really fast by now. So you can do it for 150 million SNPs within 5 minutes. Easy to do. But what people are also interested in is the variance. So is the count of the B allele increasing the variance of your phenotype? That's not that easy to be doing because it's no longer a linear regression model. It's also depending on your allele frequency. You have to have like a more common SNP to do this, but it's possible. You can do it. And the people mostly do it because they hope to find some interactions with the environment. So any other phenotype you want to look for. And this example that I brought you here, it's simply showing you there, on the first look, there is no mean effect for the SNP on the biomarker. But it's covered by the interaction with smoking. So if you would be a smoker, you would have a positive SNP effect here. And if you were a non-smoker, you would have a negative SNP effect. But because it's the combination, you only see the effect of the variance. So this is what I was coming from. And I was thinking about, okay, could we do this in one model at the same time if we had longitudinal data? So that was kind of the plan, the hope, what I wanted to do. So when we think about longitudinal GWAS, there are not that many models available. That's because we are looking at like 500,000 people and 150 million SNPs that you want to analyze at the same time. So you want a robust and fast model and not the perfect model. So what most people are using is this GMAT model, which just searches for the main effect and maybe some time interaction, so the slope or trend effect. And it's nice, it's scalable, and you can also adjust for random effects caused by the polygenetic effects that you have in your genome. So it's the correlation between individuals and the correlation between SNPs. So that's kind of working. But what you don't get in this model is the variability that we are interested in. So that's what I was looking for. So I used the simple Gamma's model. So when I say simple, I really mean just a simple R implementation of this, because the scalable algorithm didn't work for me. If anyone wants to help me getting it running, feel free. There is a try GWAS tool, but it has some own problems to make it run. And none of this, neither the R implementation nor the TriGWAS at the moment corrects for the relationship between the individuals you have in your data. So that's kind of the problem. So what I'm focusing on is really those SNP effects, the beta 0, beta 1, and the tau, so the SNP effect on the mean, the slope, and the variability, because those are the statistics I want to use later in my MBMR model. And this is actually my second part, so that's where the interesting stuff is happening now. What is Mendelian randomization? I don't know if anyone heard about that here. I mean, yes, some people have. So we want to have a causal estimate here. So we're looking for, so we have an exposure, we have an outcome, and we kind of believe there might be a causal effect of this exposure on your outcome. And if we have a really strong SNP or multiple SNPs who nicely predict our exposure, we can leverage this information and assume that this effect on the outcome is completely mediated by our exposure, and can simply say, okay, this causal effect of the exposure on the outcome is kind of the ratio of those SNP effects, because everything is mediated. So we need to assume that the SNP has no effect on any confounder. That's called pleiotropy. That's bad. We don't want that. It's nothing we can prove. It's just we can say, okay, it's plausible to assume that we don't have any pleiotropic effects. We cannot prove that because most of these confounders are unknown. We don't know them. So we can't test for something you don't know. So what I did was kind of extend this univariate model into a multivariate model by simply splitting my exposure into those 3 parts, for which I could get SNP effects in the Gammels models. So I do the Gammels, get those 3 SNP effects, get some published data for the SNP on outcome, and then simply do a linear regression model and estimate all 3 causal estimates. This sounds very easy. You only have to keep in mind that you want conditional significant instruments, and maybe there's also some problem with correlation between the instruments. But that's why I thought, okay, just do a simulation study and see what happens. I don't talk about everything I simulated because that would kind of take hours. I just selected some highlights, and I simulated an exposure that should be affected by everything, so I should have instruments for everything. That was the important part. And from the published longitudinal GMAT data, I knew that in most cases we have a high correlation between the mean and the slope, and it's always negative. So I included a negative correlation between my SNP effects on the mean and the SNP effects on the slope, but no correlation between the SNPs of SNP effect of the mean and variability, or slope and variability. And it looks great. Everything was good. So yes, we have some lower power here. So that's a power heat map. And the one indicates, yes, every single time we test for it and it should be there, it's actually there. That's very good. And only the variability in the case when the slope also has an effect is kind of lower, but it's still good. I mean, 87%, 78%, that's not that bad. It's kind of okay. And then I started to look into literature just to be sure that I get the correlation, the genetic correlation right. And yeah, it's not always the case that the variability should be independent of the mean. So we look in proteomics that we have the case that 90% of all variant SNPs are actually also mean SNPs. So they affect both of these things. And of course, those effects are correlated. I mean, you can't kill that. So I thought, okay, let's do it again. And this time include some correlation with the mean and the variability and the slope and the variability. And the good news is for the mean and the slope, it still works. For the variability, yeah, no. So when it's only the variability, we could find something. But if it's really a combination of things, then we have a really low power. So that was kind of sad. But it's the truth. I mean, you can't change when you simulate stuff, you can keep simulating, but it won't change at some point anymore. If this correlation structure exists, you have to accept you have the false negative results for the variability. So I thought, okay, just look into real data. Can we kind of make it, do we see same results in real data? And I used the UK Biobank data for this. I picked total cholesterol levels. Had I known that everyone is looking at blood pressure, I would have picked the blood pressure data. I didn't know it at that time. Maybe I can just repeat the entire stuff with blood pressure data. But for you, it's available. Go to the UK Biobank, get the GP data sets, and play with the blood pressure data. This is just example of 10 random samples, because if I show you the trajectory of every one of those 70,000 people, then you see nothing. But that's about the sample size. We have 73,000 people and a median of 7 measurements per person. Yes, and I didn't want to run a full GWAS because I was like, okay, I just want a sensitivity check if this is working. So I just picked some 350 SNPs, which should be associated with the mean level of cholesterol, cholesterol levels, according to some beta GWAS that was published 2 years ago. And so I ran for those 350 SNPs my Gamels model and checked if they are associated in this data set for the 70,000 people in the UK Biobank. And yeah, they were. I mean, not all of them. So I was kind of hoping that more of my 300 SNPs would be associated, but it's just, the meta GWAS was 1 million people. And I just have 70,000, so it couldn't really have the same power to detect all of them. And 100 is kind of a good number of instruments to work with. So I was like, okay, we have this. Let's look for outcome data. That was the coronary artery disease, and I used some published data from the cardiogram consortia, just to match them. That's what we do in the Mendelian randomization. We use different data sets for the effect on the exposure and outcome. And this is the result. It's significant. At least the mean and the slope is significant. And that was the important part for me, because that's my positive control. If this is not working, if I don't find the mean effect, then what am I doing here? Something went really, really wrong. So it's working. Most importantly, yes, we have a similar genetic correlation as in my simulation study. So it's not really surprising that my multivariate model, so my MVMR, I don't find an effect of my variability, which is most likely due to this correlation structure. So I was like, okay, let's do some cherry picking. Can I somehow create this genetic correlation that I had in my first scenario for my simulation? And of course, I had many SNPs available, so I could just cherry pick those that were strong for the mean and those that were strong for the variability and not associated with each other. So 44 instruments, that's a drastic reduction of instruments, but I want to see if it works. And yes, we find an effect in the variability. So I was like, maybe this is all just genetic correlation. That's killed the effect in the first analysis. But the problem is cherry picking. Who wants to do cherry picking of instruments? That's not what we should do, not what we want to do. So I was like, okay, I use this relative strict criteria to say we want SNPs that are not at all associated. What would happen if I would be a bit less stringent and allow a bit more significance in the other phenotype, exposure type? So I just used the factor 10 and said, let's do a bit more instruments, even when there is some weak effect on the mean, although it should be just on the variability. The correlation is not affected by that, right? It's still not no high correlation. But by increasing more weak instruments, you are, again, reducing your variability effect. So this is kind of where it's going down again. So this is where I was beginning to think about, is this even the right approach? And even if we would have a significant effect when we use more SNPs, would that be something we want to have? I don't know if you remember my first slides where I was talking about the variants, and those are good candidates for gene interactions, gene-environment interaction. Those interactions are actually pleiotropic effects, if you remember that, right? And pleiotropic effects are those things we don't want in the MVMR. So this is maybe more a way to correct for this pleiotropic effects that we can't stop them to be there. They are always there. SNPs will affect more than one trait. but maybe this way to include them in the variance is a way to correct the mean and the slope effect for those interactions. This is where I'm still working on. I haven't finished on that. This is just where my work stopped for now, and I will do some more simulations with more interaction terms and to see what happens. For now, I would just say the method seems to work, but it highly depends on this genetic correlation structure that we have, and also on what kind of SNPs, what kind of instruments do you select. And we have some open problems. We have the availability of data sets. I use the UK Biobank, and I still have those weak problems. And the UK Biobank is the biggest thing I can think of. So it will be hard to find a bigger data set to try something like that, at least for Mendelian randomization. So we'll see if any other large biobank comes with longitudinal data around anytime soon. The GAMLs package that I used in R is not really ideal for a GWAS, as I mentioned before. And the try GWAS tool that's available has its problems with the relationship structure, and also issues with running and getting the summary statistics that not just tell you it's significant. So it's doing a score test, and I really want the better estimates. So it's kind of the wrong thing to look for. So that's kind of still open problems to look into. On top of this question, is it just all pleiotropy problems and weak instrument bias due to that? And with that, I can finish my presentation. I thank you for the attention, and I'm happy to answer any questions.